Welcome to solving quadratic equations by factoring. First thing I'd like to point out to you is something called the zero product theorem. Anytime that you set out to solve an equation by factoring, you will be using something called the zero product theorem. I've written it here. The zero product theorem says if the product of two numbers is 0, then the first number is 0 or the second number is 0. Okay, let's take a look at our first problem. Here we have the product of two numbers. 2x is multiplied by 3x plus 5. So that's the product of two numbers is 0. Therefore, by the zero product theorem, either the first of the two numbers, 2x, is 0, or the second of the two numbers, 3x plus 5, is 0. Now, if 2x is 0 and you come in and divide both sides by 2, this leads you to your first solution to the problem, x equals 0. Now if 3x plus 5 is equal to 0, just solve this for x by moving 5 to the other side by subtracting 5's. And then when you divide both sides by 3, you get x equals negative 5 over 3 for a second solution. Now, what's kind of unique about example 1 is that it was set up for the zero product theorem right from the beginning. You had the product of 2x with 3x plus 5 giving you 0. That's the hypothesis of the zero product theorem, which says if the product of two numbers is 0. In most of the problems that you're asked to solve by factoring, this will not be the case. You will have to make the 0 and you will have to make the product. So let's take a look at example 2. It says solve by factoring 12x cubed equals 22x squared plus 20x. In this problem, there is no 0 on one side and there is no product on the other side. So it's up to us to make both. I'll begin by making the 0. I could make the 0 by moving the 12x cubed to the right. But if I did that, it would become negative 12x cubed, and I'd rather have a positive on my term of highest degree. So I'm going to move the other two terms to the left. If I subtract 22x squared from both sides, and subtract 20x from both sides, I get 0 on the right side, and 12x cubed minus 22x squared minus 20x on the left. And there is our 0. There's part of our zero product theorem. Now we need a product on the other side. And making products is what we call factoring. Anytime you say factoring, that means to make a product. Now, when you factor something like this, the very first thing you want to do is look for common factors. I see a 2 and an x in the first term, 2 and an x in the second term, 2 and an x in the third term. 2x is a common factor of all three terms. So pull out the 2x. Now you've pulled it out if, when you multiply back, or you pulled it out correctly if, when you multiply back, you get what you started with. So if I take 2x out of 2x squared, and then I multiply it back, or 12x squared, I'm sorry, and see that check just saved me from making a mistake there. When I take 2x out of 12x cubed, I get 6x squared. When I multiply back by the 2x, the 2 times 6 gives me 12, the x times x squared gives me x cubed. So I'll do the same thing on my next two terms, minus 11x minus 10. I'll multiply back the 2x, 2x times negative 11x, negative 22x squared, 2x times negative 10, negative 20x equals 0. Now let's see if the three-term expression can be factored. Let's just try a couple of things here. One way to get 6x squared, that's pretty common, is to multiply 3x by 2x. Now, in order to get a negative 10 for the last term, that means the center signs have to be opposite each other. So this either has to be a minus times a plus, or it has to be a plus times a minus. We'll try minus times plus, and if that doesn't work, we'll just change the two signs. Now I need to get an 11 in the middle with a 10 on the end, so I could go 5 and 2, that would give me the 10 on the end, but that gives me 15x plus negative 4x, which is positive 11x. That's the wrong center term. So I'm going to rewrite it with the center signs changed. 3x plus 2 times 2x minus 5. And that should correct the problem of center sign. Now for the inside product, I get 4x. For the outside product, negative 15x. So that gives me negative 11x, and that is the correct factoring. Now we have a product of three numbers equaling 0. So the first number is 0, or the second number is 0, or the third number is 0. And if 2x equals 0, then x equals 0, and there's one solution. If 3x plus 2 is 0, move the 2 to the other side, and you get x equals negative 2/3. And if 2x minus 5 is 0, move the 5 to the other side, and you get x is equal to 5/2. Now, just as an aside, note, when the highest degree term had power 3, I had 3 answers. When the highest degree power term here, which would be 6x squared, had power 2, I had 2 answers. One answer for each factor. Now, this third type of problem is kind of an interesting one. A lot of times when people see a problem like this on a test, they'll do the following. Divide both sides by x, and you get x squared is 25, x equals 5. Sometimes if they're really alert, they'll say x equals 5 or negative 5. But let's see what happens if we use the zero product theorem. Now, to use the zero product theorem, we're first going to have to make a 0. Again, I want my high degree term, x cubed, to be positive, so it's the 25x that I'll move. I factor out the common factor x, and what I'm left with is a difference of squares. You'll recall from your old factoring days that a difference of squares always factors, and it always factors into a product of conjugates. So I take my difference of squares, I factor it into a product of conjugates. I now have three numbers, x, x minus 5, and x plus 5, multiplied together to give me 0. So either the first number is 0, well, holy smoke, there's answer number 1. Or the second number is 0, there's answer number 2. Or the third number is 0, and there's answer number 3, again corresponding to an equation of degree 3. And you see that by using the zero product theorem, another answer comes into play, and there's absolutely no question about the other two answers. So that's a very good reason for always using that zero product theorem when you can to solve equations. Here it bought us that last solution. And that concludes the podcast.